Welcome back, everyone, to the Deep Dive. Today, we're going to be taking a look at quantum computing.
Yeah, one of the most exciting and confusing areas of research out there right now.
Absolutely. We've got a ton of articles, research papers, news stories, even some personal notes
Oh, wow.
that we're going to be going through to really try and get a grasp on this topic. Basically, we want to figure out what quantum computing is, why it matters, and what challenges are in its way.
We're going to try to cut through all the hype and see what this technology is really capable of.
Exactly. So maybe we can just start with the basics.
Yeah, sure.
Like, how does a quantum computer actually differ from the computer that I'm using right now to record this?
That's a good question. It all boils down to how they process information. So the computer you're using relies on bits, which are either a 0 or a 1.
Like an on or off switch?
Exactly, just like a light switch. But quantum computers use something called qubits, and this is where things get really interesting.
Yeah, I've heard of those.
So a qubit can be a 0, a 1, or both at the same time.
Hold on, both at the same time. How is that even possible?
It's a mind-boggling concept called superposition. It's one of the fundamental principles of quantum mechanics. Imagine a coin spinning in the air
Yeah.
until it lands its both heads and tails simultaneously. That's kind of similar to what's going on with a qubit.
So it's like the qubit is in this weird state of uncertainty until we actually look at it.
You got it. When we measure it, it collapses into either a 0 or a 1, but before that, it holds both possibilities.
That is so strange. And there's also that other wild concept, I think it's called entanglement.
Oh, yeah. Where two qubits are somehow linked even if they're miles apart.
Right.
It's one of the most baffling aspects of quantum mechanics.
Yeah, it sounds like something out of Star Trek.
It kind of is. Imagine two of those spinning coins we were talking about.
Mm.
When one lands on heads, the other instantly flips to tails no matter how far apart they are. It's almost like they're communicating faster than the speed of light.
So how do these really weird quantum phenomena actually help us solve problems?
Well, think of it this way. A classical computer is like trying to find your way out of a maze.
Okay, I've been in a few of
You,
theirs.
you have to explore each path one at a time.
Yeah.
But a quantum computer can explore all possible paths simultaneously. It's like having a million tiny explorers all working at the same time.
Oh, wow.
This massive parallel processing power, combined with superposition and entanglement, allows quantum computers to tackle problems that would take classical computers billions of years to solve.
So are we all going to be throwing out our laptops and getting quantum desktops anytime soon?
Not so fast. Quantum computers aren't meant to replace our everyday devices. They're more like specialized tools for specific, highly complex problems that classical computers just can't handle.
Okay, so they're not going to be streaming Netflix anytime soon.
No, probably not.
So what kind of problems are we talking about?
Well, imagine simulating complex molecules to design life-saving drugs or creating brand new materials
Really?
with unheard of properties, things that we can't even dream of right now.
That sounds pretty amazing.
It does. And that's not all. Think about cryptography. Quantum computers have the potential to break the encryption that protects our online data.
Oh, wow.
That's a huge deal. They could also revolutionize fields like finance and logistics by finding optimal solutions to incredibly complex problems.
So you're saying maybe no more traffic jams.
Maybe one day. But let's not get ahead of ourselves. Building and using quantum computers is incredibly difficult.
Right, I was going to ask about that. What are some of the major challenges that are in the way?
Well, first off, qubits are incredibly fragile, like super delicate snowflakes.
Really?
The slightest disturbances, like heat or vibrations, can cause them to decohere, which basically means they lose their quantum state.
So all that cool quantum stuff just vanishes.
Pretty much. So scientists have to create incredibly controlled environments, nearly absolute zero temperatures, just to keep these qubits stable.
Wow,
It's like trying to build a house of cards in a hurricane.
that's pretty tough.
And even then, they're still prone to errors.
So not only are they super fragile, but they make mistakes.
It's a constant battle. And to make things even more difficult, scaling up these systems, adding more qubits without sacrificing stability, is a monumental task.
It sounds like a Herculean effort just to get these quantum computers to work at all.
Yeah, it really is. But that's just the beginning. We also have to figure out how to program these machines.
Oh, right. So that's probably not easy.
It's a whole other challenge altogether, and that's what we're going to be talking about next.
Okay, well, let's do a quick recap then. Quantum computers use qubits, which can be both 0 and 1 at the same time thanks to superposition, and they also leverage entanglement, that spooky connection between qubits, to achieve incredible processing power. Now, this opens up possibilities for solving really complex problems in medicine materials, science cryptography, and so much more. But as we've learned, building these quantum marvels is no easy feat. So stay tuned as we explore the equally daunting task of programming these strange and powerful machines. Okay, so we've talked about how difficult it is to build these quantum computers,
Yeah.
but now we have to figure out how to program them. That sounds even harder.
It's definitely a whole other challenge. Programming a quantum computer is not just about learning a new programming language. It requires a completely new way of thinking.
All right, ready. What makes it so different from the programming we're used to?
Well, in classical computing, we use logic gates, like AND or OR, and not to manipulate bits. But in quantum computing, we use something called quantum gates to manipulate qubits. And these take advantage of superposition and entanglement.
So instead of just simple on-off switches, we're dealing with these fuzzy probabilistic qubits. How do you even begin to program something like that?
It's a big mind shift. You have to think in terms of probabilities and quantum states. So instead of writing lines of code, you're essentially designing quantum circuits. These are sequences of these quantum gates that act on the qubits.
So it's almost like quantum programmers are more like circuit designers or even choreographers. They're orchestrating these complex dances of qubits.
That's a great way to put it. And just like learning a new dance, mastering quantum programming requires a really solid grasp of the underlying principles. In this case, things like linear algebra and quantum mechanics.
So not exactly something you can pick up on YouTube.
No, not really.
Are there even any specific programming languages for this quantum world?
There are a few that are becoming pretty popular. There's Qiskit from IBM Circ, from Google and Microsoft's Q Sharp. They provide tools and frameworks for building and manipulating these quantum circuits.
Okay, so we have specialized languages and this whole new way of thinking about programming.
Yeah.
What about algorithms? I know there's one called Shor's algorithm that's supposed to be able to break encryption codes.
Ah, yes. Shor's algorithm. That's one of the most famous ones. It can factor large numbers exponentially faster than any classical algorithm we know of.
And why is that so important?
Well, it's a big deal for cryptography because a lot of encryption schemes rely on the difficulty of factoring large numbers.
So does that mean if we had a powerful enough quantum computer, Shor's algorithm could crack the codes that protect like our online banking, our communications, pretty much everything?
In theory, yes. But building a quantum computer that powerful is still a long way off.
Okay, so maybe our secrets are safe for now. But what about other algorithms? Are there any that could be used for, like, searching through massive databases?
Yeah, actually. There's Grower's algorithm. It's designed specifically for searching unsorted data, and it can speed up searches quite a bit compared to classical algorithms, especially when you're dealing with really, really large data sets.
So for like researchers or anyone dealing with huge amounts of data, Grover's algorithm could be incredibly useful.
Absolutely. It's like having a super-powered search engine, way faster than anything we have today.
Okay, starting to see the potential here.
Yeah.
But from what I've been reading, there's more to quantum programming than just these new languages and algorithms. It seems like there are some pretty fundamental challenges because of the very nature of quantum mechanics.
You're exactly right. One of the biggest hurdles is that quantum computers are inherently probabilistic.
Probabilistic, what does that even mean?
It means that instead of spitting out a single definite answer, like a classical computer does, a quantum computer gives you a range of possible answers,
Okay,
each with a certain probability.
so it's kind of like rolling the dice. You can't predict exactly what you're going to get, just the odds of different possibilities.
That's a good analogy. So this means that you have to run the same program multiple times and then analyze the results statistically to actually get a meaningful answer. And that adds a whole other layer of complexity.
Wow. So you not only have to wrap your head around this new way of programming, but you also have to deal with this inherent uncertainty.
And on top of that, there's another tricky thing we need to think about: measurement collapse.
Measurement collapse. That doesn't sound good.
Remember we talked about how qubits exist in a superposition of states until we measure them?
Yeah, like that spinning coin that's both heads and tails until it lands.
Right. Well, when we measure a qubit, we force it to collapse into one definite state, either a 0 or a 1. And the problem is this collapse can destroy the very information that we were working with.
So it's like we're trying to study a soap bubble, but the act of observing it makes it pop.
Exactly. It's a very delicate dance. You have to be super careful about when and how you measure these qubits so you don't accidentally destroy the information you need.
Okay, so probabilistic outputs and measurement collapse. Anything else I should be worried about?
We can't forget about noise and errors. Quantum systems are incredibly sensitive to anything and everything around them, and the tiniest disturbance can throw off the calculations.
So on top of everything else, we have to worry about these delicate systems being influenced by their surroundings.
Basically, yeah. Filtering out noise and correcting errors is a huge part of quantum programming. It's like trying to have a conversation in a really loud and crowded room.
All right, I think I'm starting to get a headache just thinking about all this. It's hard enough to build these quantum computers, but then programming them involves this whole new way of thinking. You've got probabilistic outputs, measurement collapse, and a constant battle against noise and errors. It's just mind-boggling.
It's a huge undertaking for sure. But the potential rewards are so big that researchers everywhere are pushing forward, trying to unlock the power of this technology.
Well, they've definitely got their work cut out for them. So we've talked about all these immense challenges of building and programming these quantum computers. Now I'm curious, what can we actually do with them? What are the real-world applications?
That's the question everyone's asking. And that's what we'll be diving into next.
All right, so welcome back, everyone, to the show. We just finished going over the ridiculous challenges of actually programming these quantum computers.
So it's tough stuff.
But now I think it's time to answer the big question.
Yeah.
What can we actually do with them? What are the real-world applications? I mean, we all going to have quantum phones and laptops soon.
Well, that's the million-dollar question, isn't it? We are still really early on,
Right.
but the potential applications are just massive and so exciting.
Okay, well, let's just get this out of the way now.
Yeah.
Will these quantum computers actually replace, like, my laptop and phone?
Yeah.
Should I hold off on buying that new iPhone?
That's a super common misconception.
Yeah.
Quantum computers are not going to be replacing our everyday devices anytime soon. They're really good at specific types of tasks that classical computers struggle with, but they're not designed for things like browsing the internet or sending emails.
This is more about working together.
Yeah, exactly, like a powerful partnership.
Yeah.
Classical computers are going to continue to be great for things like browsing the internet, sending emails, and even a lot of complex simulations. Quantum computers are going to step in for those really specialized problems that require that unique power of superposition and entanglement and these special algorithms.
So we're not ditching our laptops anytime soon.
Yeah.
But we are adding another really powerful tool to the toolbox.
Yeah.
Okay, so what areas could we see this quantum advantage really shine in?
Well, one of the most exciting areas is drug discovery and materials science.
Oh, yeah, I've heard about that.
Imagine being able to simulate how molecules interact
Uh-huh.
at the atomic level.
So we wouldn't need to do all that trial and error in a lab.
Yeah, instead of spending years in the lab,
Wow.
we could design new drugs, new materials with unbelievable precision.
Or we could create, like, super effective medicines
Yeah,
with fewer side effects.
exactly. Or even revolutionary materials for anything from renewable energy
Oh, wow.
to aerospace.
It seems like we could get a much deeper understanding of how the world works at the smallest level.
Absolutely.
That's amazing. What about other fields? We talked about cryptography and how quantum computers could be used to break those codes.
Oh yeah, Shor's algorithm. If we can actually build a quantum computer powerful enough to run it, it could crack the encryption we use for like all secure communication and online transactions.
I mean, that sounds a little scary.
It's definitely something to think about. It means we need to rethink cybersecurity,
Right.
but it also means that we have an opportunity
Yeah.
to make new and better ways to protect our data.
So it's like a cybersecurity arms race with these quantum computers pushing things forward.
Pretty much, and we've only just scratched the surface here. Quantum computing could also be huge in areas like finance or logistics, where figuring out the most efficient way to do something is super important.
You mentioned like optimizing traffic flow.
Oh yeah. No more soul-crushing commutes. Quantum computers could help us design way more efficient transportation systems, smoother supply chains, better financial models, and even help us make advancements in artificial intelligence.
It sounds like the possibilities are almost endless.
Yeah, the potential is really huge.
But it's clear that we're just getting started. What are some of the big hurdles that we still need to overcome to make all of these applications a reality?
Well, we've talked about a lot of them already, like actually building these stable quantum computers,
Yeah.
making them bigger, developing quantum software that works,
Right.
and figuring out how to deal with all that noise and errors. But there's also some bigger challenges out there, like figuring out how to teach people how to use these machines
Yeah.
and setting up some ground rules for how we're going to use this technology ethically.
So we can make sure it's used for good.
Exactly. As we keep pushing the boundaries of quantum computing, we need to be super careful about the potential consequences and make sure that it helps everyone.
Well, I have to say, after this deep dive, I'm feeling a little overwhelmed, but mostly excited about the possibilities.
Yeah, it's pretty incredible, isn't it? This is like revolutionary technology
Yeah.
that could change the world in ways we haven't even thought of yet.
It really makes you think about what's possible.
Yeah, it challenges everything we know about computing and physics.
So, as we wrap up this episode, what is the one thing you want our listeners to take away from all this?
Just stay curious. Quantum computing is changing so fast, and who knows, maybe one of our listeners will be the one to make the next big breakthrough.
That's a great point. And that is it for this deep dive into the world of quantum computing. Until next time, stay curious, everyone.